Good day to everyone present. My name is Kiyolin Perumal, and I'll be giving a takeaway talk on the evolution of quantum computing. Now, I don't know about you guys, but I like to start off anything new by consulting my trusted friend, Wikipedia. So according to Wikipedia, quantum computing is a type of computing that utilizes quantum mechanics phenomena such as superposition, interference, and entanglement to perform computations. And the machines that perform quantum computing are called quantum computers. Now, quantum computers may seem like a very recent development. However, the initial idea behind a quantum computer was proposed in the 1980s by physicist Richard Feynman and mathematician Yuri Manin. And it is thanks to them that I have something to speak about. Quantum computers have the potential to solve some of the world's most complex problems that are beyond the reach of even the most powerful supercomputers in existence today. It's important to note, though, that quantum computers will not replace classical computers, but their way of performing computations allow them to solve certain problems that classical computers cannot in a reasonable amount of time. This advantage that quantum computers have comes from their ability to be in a large number of states at the same time, whereas classical computers can only be in one state at any given time. Now, before we have a look at why this is so, it's important to understand how quantum superposition, interference, and entanglement works. Quantum superposition is the ability of a quantum system to take on multiple states at once. An example that some of you may be familiar with is Schrödinger's cat. Now, very quickly, this theoretical experiment places a living cat in a steel box with a radioactive trigger and a vial of poison. If the radioactive substance decays, then the trigger will break the vial of poison, killing the cat. If the radioactive substance does not decay, then the cat remains alive. But without opening the box, we don't know, and in fact cannot know, the state of the cat. And so the cat is said to be both dead and alive. In quantum mechanics, this state is called a superposition. And it's the act of opening the box is called taking a measurement. And it is only then that we can say whether the cat is dead or the cat is alive. Now, classical computers store data in bits, where each bit can be either a 0 or a 1. And these bits behave sort of like a switch, where the value corresponds to either an off or on electrical signal. Whereas quantum computers utilize quantum bits or qubits, which can be any subatomic particle like an electron or a proton. And just like classical bits, qubits must have two distinct states, such as whether the spin of an electron is spin up or spin down. And as a visualization, you can think of them as having an arrow in a 3D space. If the arrow points up, then it's in the 0 state. And if the arrow points down, then it is in the 1 state, just like a classical bit. But quantum bits also have the ability to be in a superposition state, which is when the arrow points in any other direction. Now, this superposition state is a combination of the basis states 0 and 1. And it's important to note that when we take a measurement, the superposition collapses into one of the basis states. So it'll end up being either 0 or 1 when we take a measurement, but which state we end up with depends on a probability estimate that is determined by the direction of the arrow. If the arrow is more to the top, then it is more likely that the measurement will give us the 0 state. Now, all of this relates to the workings of a single qubit. Now let's look at what happens when we have multiple qubits. In a classical computer, the bits are independent of each other. So changing the value of one bit doesn't affect the value of the bit next to it. With quantum bits, quantum entanglement causes the state of one qubit to be tied up to the state of another qubit. So suppose we have two qubits, A and B, in an entangled state. When A has spun up, then B has spun down. And when A has spun down, then B has spun up. So by virtue of the entanglement, they are always opposite. Then suppose we move A into the superposition state where it is both up and down. And now we attempt to flip the state of B. Now, because A is in the superposition state, then the state of B both flips and doesn't flip. The situation now is that we don't know what state each qubit is in, but what we do know is that they will always be opposite in direction when the measurement takes place. And this is true no matter how far apart the qubits are. You'll notice that it doesn't even make sense to consider the qubits individually anymore, because they've become part of a larger quantum system that's in a superposition state. And this is special because it represents a kind of non-classical computer state in the sense that we have two bits that have no value just because we don't know the value, but at the same time, they have the opposite value. This also allows for another interesting situation where we can infer this state of both bits by only measuring either A or B and never even checking the other. But how does being in many states at the same time help us? And this takes us to quantum interference. Now, the qubit itself can also be described by a quantum wave function. When many qubits are entangled, all of their wave functions are added together using constructive and destructive interference to form an overall wave function. So in solving a problem on a quantum computer, you need to use constructive interference of qubits to increase the probability of the correct answer, and you need to use destructive interference to decrease the probability of the incorrect answer. Now, all of these changes, now this nature of quantum bits causes them to have some differences in the way they store information. So suppose we have two classical bits. And between these two bits, there are four possible states that the computer can be in. 0 being 0, 0, 0, 1, and 1, 1, 0, and 1, 1. Now from these four states, the computer can only ever be in one state at any given time. But a quantum computer can explore all four states at the same time. And it's easy to understand this if we consider that two classical bits only store 2 bits of information. For example, if we take the value 1, 0, in order for me to determine that that is the value, I only need the value of the first bit, which is 1, and the value of the second bit, which is 0. But with the quantum computer, I actually need 4 different values. And these 4 values being the 4 coefficients that give the probability of each of these 4 states occurring. And so in this way, we can see that 2 quantum bits actually contain 4 classical bits of information. If we take 3 quantum bits, that now contains 8 classical bits of information. When we reach 100 qubits, which is about how many qubits the quantum computers of today have, then there are very, very large number of states, and this increases exponentially. If we have n number of qubits, then there are 2 to the n number of possible classical states that the quantum computer can be in and can be in at once. Now let's have a look at the issues in the development of quantum computers. As we've already seen, the amount of information that the quantum computer has increases exponentially as more qubits are added. This also means that the complexity of the quantum superposition state also increases exponentially with each new qubit that is added. This means that it becomes increasingly difficult to write quantum algorithms that produce the desired result. Another issue affecting quantum computers is noise, and this noise can be anything that affects the accuracy of the measurement, the accuracy of the result from a measurement. Noise in quantum computers leads to something called decoherence, where the superposition of even a single qubit is affected, and due to quantum entanglement, causes the entire system to be inaccurate. And it's easy to consider how the kinetic energy of subatomic particles and heat is an issue if we consider a room full of people who are all speaking at the same time. If you are in that room and trying to have a conversation with someone, it would be very hard to hear the other person just because of the interference from the environment. An easy solution to this problem would just be to remove all the disturbances. And we can attempt to achieve this with a quantum computer by placing it in an enclosure that isolates it from the external environment, thus ensuring that the qubits do not get entangled with foreign particles. Then the temperature inside the enclosure is cooled to near absolute zero to reduce the kinetic energy of the subatomic particles to a point where they move slowly enough so that an accurate measurement can be taken. But even with these methods being employed, it is still not enough to tame the behavior of quantum bits. And so we need to resort to error correction and various other methods to increase accuracy. Now, why should we even bother about this? And I suppose this is the most important part. So first up, we have quantum simulation, which deals with simulating things like chemical reactions with the behavior of electrons. Due to the quantum nature of quantum computers, they have a big advantage over classical computers in this field. Quantum computing also has some concerning implications in cybersecurity. There exists a quantum computing algorithm known as Shor's algorithm, which solves the problem of prime factorization in such an efficient way that if given a computer with enough qubits, it could theoretically break RSA encryption very easily. So there are also applications in machine learning, AI, and financial modeling, and many other fields of study. As long as the problem can be correlated to the behavior of quantum mechanics, then there's a possibility for quantum application. That brings us to the end of this talk. Thank you.